let's begin to build up this model of gravity. Some observations that we've made so far. You can talk about how the force of an object depends on the mass, F equals ma. So we're some block of a mass m, and we feel an acceleration g down towards the Earth planet, down towards the surface of the Earth. Now, if we say double the mass, well, we'll double the force. Imagine someone who is 50 kilograms charging at you, say like a 10-year-old child, maybe a young teenager, versus someone who is 100 kilograms. These would be like big football or rugby players charging, slamming into you, right? So we know that mass is proportional to the force. Doubling one will double the other. Well, let's look at it differently. Instead of doubling, say, the mass of you or the object throwing at you, let's move to a different planet. Let's go to a planet that's twice as massive. And we'll find that doubling the mass of Earth, if you double the mass, the gravitational pull pulling you down, once again, we're going to double the force acting on you. So let's start stitching this together. We're postulating that there is this gravitational force, that there has to be something out there. And so we're going to say it's some stuff times the products of the masses of the objects, M1, M2. Continue on. Kepler knew that the sun had an influence on the planets. What Kepler called influence, Newton formalized as a force now. And remember, how did Kepler get to his concept of influence? How did he know it was there? Well, remember his laws. Sun sits at a focal point. The closer you are to the planet, you have to move faster. You swing by rapidly when you're close. And when you go far away, when the planet's far away, you have to slow down. That influence decreases based on distance. So we're going to say the gravitational force has to be some stuff times the product of masses of the things involved. In this picture here, the sun will be one mass and the planet will be the second mass. And it's going to be dependent on the distance squared. And we're not going to go into the details why postulate the squared, other than the shortcut of saying, well, it works. There are more reasons why we want to postulate the squared factor there. But we're going to ignore those details for now and just say that we know that 1 over the distance squared is going to be what's producing our gravitational force that we're measuring. Now, we just created this inverse squared law, and I want to talk about it. I think it's really important to be able to model and draw the pictures. And if you're not comfortable, if you're not familiar with this thing, what are the tools you can use to figure out how to make a picture of it? So, how do I plot y equals 1 over x squared? Plug in values. Pick the easy ones, right? Start with 1, right? What is 1 squared? It's 1. Well, what's 1 over 1? It's 1. All right, easiest. Now let's try 2, right? What is 2 squared? That's going to be 4. So now say, well, what's 1 divided by 4? Well, that's going to be 1/4, or 0.025. 3, right? 3 squared. 3 squared is 9. 1 divided by 9, it's close to 1 divided by 10, so it's something close to 0.1, right? So, as x gets bigger, y is getting smaller and smaller. Now let's try 0.5. Let's try this one, right? 0.5 is 1 over 2. So when we plug in 0.5, we say 1 over 2. Square that. Well, 1 over 2 in the denominator flips to 2 in the numerator. So I have a 2 squared in the numerator. What's 2 squared? 4. Done. Right? So if you have a value smaller than 1, you just keep making bigger and bigger numbers. And there's our inverse squared law plotted out, right? Right. As you approach 0, this curve is just going to keep blowing up towards infinity, getting bigger and bigger. And as you go far away, as the distance between the objects is getting bigger and bigger, the force between them is going to die down. With our discussion on the inverse squared law dealt with, we now can present Newton's law of gravity. Right? And it says that the force between two objects goes as a gravitational constant, the product of their masses, divided by the distance between them squared. Sometimes heard as r squared. So you'll have an m1 and m2. By Newton's third law, they'll have equal forces pulling each other. Both objects are always trying to pull towards each other. So let's look at that gravitational constant. I'm going to call this big G, or the universal gravitational constant. It is related to little g, but it is not an acceleration. Right? So the universal gravitational constant goes to 6.67, 10 to the minus 11th. That's what's really going to matter for us. This 10 to the minus 11th Newtons meters squared per kilogram squared. And if you ever have a hard time remembering the units on this thing, go back to the formula. Right? The force has to be in newtons. Up here I have a kilogram times a kilogram. So kilogram squared up here. Radius squared. So that's meters squared. So G, the units on G is to make that this whole thing multiplies out into a Newton again. So here's just a rotated perspective of that. As the radius increases, that force between them is going to have to go down. And no matter what, gravitational force is always attractive. If you take any two objects that have mass, there is a force between them. It is a law of the universe. There will be this attractive gravitational pull between the things. If we double the mass of one object, take m2 and make it 2m2, well, that's going to double the force. And by the third law, Newton's third law, right, equal and opposite forces. Equal, they both have the same amount of force between them, and opposite because they're pulling in opposite directions. Alternatively, we could double the distance, right? Take one m2 a distance r away, and now set them distance 2r away. And because it is an inverse squared law, doubling the distance is going to reduce the force between the two objects.